Arumugalakshmi. Today we are going to discuss the problems in Heat and Thermodynamics lesson. Lesson 8 in class 11 physics. The first problem, calculate the number of moles of air in an inflated balloon at room temperature. The radius of the balloon is 10 cm and the pressure inside the balloon is 180 kilopascal. So first we will list out the given data. The given data are pressure is 180 kilopascal, which is equal to 180 into 10 power 3. Kilo is 10 power 3. So it is 10 power 3 Pascal. From the radius we can find the volume. The volume formula is V is equal to 4 by 3 pi r cube. The volume of a sphere we use. So here you can substitute R is equal to 10 centimeter and the real gas constant R value is 8.314 joule per mole per Kelvin. The temperature is given as 27 degrees Celsius, which we have to convert it into Kelvin, which is the SI unit. So we have to add 273 to 27. So the answer will be 300 Kelvin. So these are the given data. The formula what we are going to use is the ideal gas equation, which is PV is equal to mu RT. Here we have to calculate the number of moles. So we rearrange this formula for finding mu as mu is equal to PV by RT. Now substituting the pressure value, volume value, real gas constant value, temperature value in this equation and further simplifying, we will get the answer for number of moles approximately as 0.3 mole. Mere formula substitution problem. Now the second problem. In the planet Mars, the average temperature is around minus 53 degrees Celsius and the atmospheric pressure is 0.9 kilopascal. Calculate the number of moles of the molecules in unit volume in the planet Mars. Is this greater than in the Earth? So the temperature is given as minus 53 degrees Celsius. Once again this you have to convert it into Kelvin. So by adding minus 53 plus 273 which gives 220 Kelvin. And the pressure is given as 0.9 into 10 power 3 Pascal. The volume is unit volume. So the answer is 1 meter cube. So number of molecules, we use our ideal gas equation. We will reverse that formula and the formula for mu is PV by RT. Substituting the given values, we will get approximately the value of mu as 0.49 moles. Now the third problem. An insulator container of gas has two chambers separated by an insulating partition. One of the chambers has volume V1 and contains ideal gas at pressure P1 and temperature T1. The other chamber has volume V2 and contains ideal gas at pressure P2 and temperature T2. If the partition is removed without doing any work on the gases, calculate the final equilibrium temperature of the container. So we will have T as the equilibrium temperature and N1 and N2 are the number of moles in the vessels 1 and 2 respectively. As there is no loss of energy, the number of moles in A and B before mixing will be equal to number of moles after mixing. So you know the formula for moles is 3 by 2 NKT. So before mixing it will be 3 by 2 N1 R1 T1 for chamber A. For chamber B it will be N2 3 by 2 RT2. So after mixing it will be N1 plus N2 3 by 2 RT. So using this formula we are going to find the value of final temperature. So the derivation is as follows. So the equation is n1 into 3 by 2 rt1 plus n2 into 3 by 2 rt2 is equal to n1 plus n2 3 by 2 rt. So cancelling the common terms, we get the expression as n1 t1 plus n2 t2 is equal to n1 plus n2 into t. Our aim is to find the value of capital T. So having capital T on the LHS, the remaining terms you take it to the RHS. So the equation becomes T is equal to n1 t1 plus n2 t2 divided by n1 plus n2. Now substituting the n1 n2 values in the above equation, we will get the final expression for T. N1 value we know using our ideal gas equation, which is P1 V1 by RT1, and N2 is equal to P2 V2 by RT2. Substituting this in the temperature, you get the expression as T is equal to P1 V1 divided by R into T1 plus P2 V2 divided by R T2, the whole multiplied by T2 divided by N1 plus N2. Here if you see in the numerator, T1 is in the numerator and T1 is also there in the denominator. So you can cancel this. Similarly, in the second term also, T2 is in the numerator and T2 is also there in the denominator. So you can cancel this T2. So finally we will be getting the equation as P1 V1 divided by R plus P2 V2 divided by R, the whole divided by, once again here instead of N1 and N2, we have to substitute the values P1 V1 divided by RT1 plus P2 V2 divided by RT2. Now, see this term R, capital R is common in numerator and denominator. So what you have to do is, the R you have to take it common outside in the numerator and denominator, and you can cancel those two terms. So the next equation will be T is equal to P1 V1 plus P2 V2, the whole divided by P1 V1 by T1 plus P2 V2 by T2. R get cancelled. Now what you have to do is, numerator you can't do any change. Denominator we have a fraction. So denominator we are going to take LCM and do the cross multiplication. Cross multiplication you know, that is P1 V1 into T2 plus P2 V2 into T1, the whole divided by T1 T2. This is how you do LCM and you do cross multiplication and you solve this equation. Now T becomes T is equal to P1 V1 plus P2 V2 the whole divided by P1 V1 T2 plus P2 V2 T1 the whole divided by T1 T2. Now the denominator is T1 T2. So denominator will go to the numerator. Hence the equation becomes T1 T2 into P1 V1 plus P2 V2 the whole divided by P1 V1 T2 plus P2 V2 T1. This is the final expression for temperature. The fourth problem is, the temperature of a uniform rod of length L having a coefficient of linear expansion alpha L is changed by del T. Calculate the new moment of inertia of the uniform rod about the axis passing through its center and perpendicular to the axis of rod. So you know that the moment of inertia of a uniform rod of mass m and length L about its perpendicular bisector. This formula we have discussed in the volume 1. So I will be equal to 1 by 2 m L squared. Now the length is increasing. So increase in length of the rod when the temperature is increased by del T is given by, the formula for new length is given as L dash is equal to L into 1 plus alpha L into del T, where alpha L is the coefficient of linear expansion. Now this expression is the expression for new length. So this length value we have to substitute in the moment of inertia formula. Instead of L, we have to substitute L dash. So the new moment of inertia equation becomes I dash is equal to m L dash square divided by 12. Now instead of L dash we have to substitute L into 1 plus alpha L into del T. So substituting we get m divided by 12 L squared into 1 plus alpha L into del T the whole squared. Now, m divided by 12 into L squared is nothing but the expression for moment of inertia of the rod before the length is increasing. So, instead of m divided by 12 into L squared, we can substitute I, where I is equal to 1 by 12 m L squared. Now substituting this value, you get the new expression for moment of inertia as I dash is equal to I into 1 plus alpha L into del T the whole square. This is the final expression for new moment of inertia. Now the fifth problem. Draw the TP diagram where pressure is taken on x-axis, temperature is taken on y-axis. Then VT diagram where temperature is taken on x-axis and volume is taken on y-axis. Diagram for isochoric process, isothermal process and isobaric process. First we shall draw the PT diagram for isochoric process. So you can see x-axis temperature is taken, y-axis pressure is taken. So as the temperature is increasing, see the graph, as the temperature is increasing, the pressure is also increasing. So it is a straight line. This is the PT graph. Now the VT diagram. VT diagram, in x-axis volume is taken, y-axis temperature is taken. Generally in isochoric process the volume will be constant. So if the temperature is increasing from T1 to T2, if the temperature varies, the volume will be still a constant only, which is V0. Now we shall draw the diagram for isothermal process. You know that for isothermal process the temperature is constant. So here in x-axis you are taking temperature, y-axis you are taking the pressure. See the diagram, when the pressure is increasing from P2 to P1, the temperature is constant. So you get a straight line. The graph for PT curve for isothermal process is a straight line parallel to y-axis. Now the VT diagram. So for drawing the VT diagram, along x-axis the volume is taken, along y-axis temperature is taken, and once again in isothermal process the temperature is constant. So when the volume is increased from V1 to V2, the temperature remains the same. So the graph is a straight line parallel to the x-axis. This is the VT diagram for isothermal process. Next, for the isobaric process. Isobaric process, we know that the pressure will be a constant. So for a PT diagram where temperature is taken in x-axis and pressure is taken on y-axis, when the temperature is increasing, the pressure remains the constant at P0. So the graph is a straight line parallel to the x-axis. Now the VT diagram. In VT diagram, for isobaric process, we know that the pressure remains the constant, but volume and temperature can vary. So here, when the temperature is increasing from T1 to T2, the volume increases from V1 to V2. So the graph for VT diagram is a straight line passing through the origin. Thus, we have drawn the TP diagram and VT diagram for the isochoric process, isothermal process and isobaric process. The sixth problem. A man starts bicycling in the morning at a temperature around 25 degrees Celsius. He checked the pressure of the tire, which is equal to be 500 kilopascal. Afternoon, he found that the absolute pressure in the tire is increased to 520 kilopascal. By assuming the expansion of the tire is negligible, what is the temperature of tire at afternoon? We will start this problem with the ideal gas equation, which is PV is equal to nRT. So the P1 value is given as 500 kilopascal, T1 is 25 degrees Celsius, which has to be converted into Kelvin because Kelvin is the SI unit of temperature. So to convert to Kelvin, you have to add 273. So 25 plus 273, which is equal to 298 Kelvin. This is the T1 value. P2 value is 520 kilopascal and T2 value only we are supposed to find, that is the temperature of the tire at afternoon. So morning, all the data in the morning is recorded as P1 T1 and afternoon it is recorded as P2 V2 and T2. So we will use the ideal gas equation as P1 V1 is equal to N into R into T1. For the afternoon process, it will be P2 V2 is equal to N R into T2. So we know that the expansion of the tire is negligible, that is volume remains constant. So we can rearrange the equation as P1 V1 by T1 is equal to P2 V2 by T2. So, since the volume is constant, you can cancel V1 and V2 on the equation both the sides. So, the equation becomes P1 by T1 is equal to P2 by T2. We are supposed to find the value of T2. So, once again rearrange this equation for T2. We get T2 is equal to P2 by P1 into T1. Now, substituting the values of P2, P1, T1 from the given data, we will get the answer as 309 Kelvin. This you can convert it into Celsius by subtracting 273. So the answer is T2 value is equal to 36.9 degrees Celsius. Now the seventh problem. Normal human body of temperature is 98.6 degree Fahrenheit. During high fever, if the temperature increases to 104 degree Fahrenheit, what is the change in peak wavelength that emitted by our body? We have to assume our human body as a black body. We know that normal human body temperature is 98.6 degree Fahrenheit. Here the unit of temperature is given in Fahrenheit. So before we go into the problem, we have to convert this Fahrenheit into Kelvin. So we know the formula how to convert Fahrenheit into Kelvin as F minus 32 divided by 180 is equal to K minus 273 divided by 100. This is the formula of conversion from Fahrenheit to Kelvin. Now substitute the Fahrenheit value as 98.6. In this equation we get 98.6 minus 32 the whole divided by 18, which is equal to K minus 273 divided by 10. This K value is the Kelvin value which we have to find. Here 180 and 100 in the before equation we have cancelled the 0. So only it is 18 and 10. Now what you have to do is you have to do the cross multiplication. That is F minus 32 into 10, which is equal to K minus 273 into 18. So when you do the cross multiplication, we have 10 into 98.6 minus 32 is equal to 18 into K minus 273. So take 10 inside the bracket, you get 986 minus 320 is equal to 18K minus 4914. So mere mathematics, 18K is equal to 666 plus 4914, you get 18K is equal to 5580. So the value of Kelvin is equal to 310. So 98.6 degree Fahrenheit is equal to 310 Kelvin. Now using the Wien's displacement law, the maximum wavelength is given by B by T, which is equal to 2.898 into 10 power minus 3 divided by temperature value. Now only we had found that it is 310. So dividing by this, you get the maximum value of wavelength as 9348 into 10 power minus 9 meter. 10 power minus 9 is called as nano. Hence the value of lambda maximum is 9348 nanometer. This is at temperature 98.6 degree Fahrenheit. Now during high fever, the temperature is 104 degree Fahrenheit. Once again, you have to convert this 104 degree Fahrenheit into Kelvin, which is given as 313 Kelvin. Now for this, we will find what is the wavelength using the Wien's displacement law. Lambda max is equal to B by T. B value is a constant, which is 2.898 into 10 power minus 3 divided by the temperature, which is 313 Kelvin. So the answer is 9259 into 10 power minus 9 meter. So once again 10 power minus 9 is nano, hence the value of wavelength is 9259 nanometer at 104 degree Fahrenheit. Now the eighth problem. In an adiabatic expansion of the air, the volume is increased by 4%. What is the percentage change in pressure? The adiabatic constant value is given as 1.4. We know the equation for adiabatic processes. P V power gamma is a constant. Now here they have given that volume is increasing. So what you have to do is we have to differentiate this equation. P V power gamma is equal to constant. We have to differentiate. So how to differentiate? We use UV formula. So in differentiation of UV is equal to UdV plus VdU. That is, you have got two terms. When you differentiate the first term, the second term is considered to be a constant. And when you differentiate the second term, the first term will be a constant. So using this differentiation method, you get P. First, P is kept as constant. Now you have to differentiate V power gamma. Differentiation of V power gamma is gamma into V power gamma minus 1 into dV plus. Now V power gamma is kept as constant and pressure you have to differentiate. So differentiation of pressure is dP. So this is equal to 0. Now take the second term to the equation that side. So it becomes a negative term. So P into gamma into V power gamma minus 1 into dV is equal to minus dP into V power gamma. After this, mere mathematics, mere rearrangement. Just follow the steps. Now what you have to do is, in the LHS, you have got V power gamma. That V power gamma, we are taking it to the LHS, and in LHS you have got P. This P alone I am taking it to the RHS. Just a small rearrangement. So we get gamma into V power gamma minus 1 dV by V power gamma is equal to minus dP by P. Yeah. Now in the LHS, V power gamma is in the denominator. That I am taking it to the numerator. So it comes as V power minus gamma. So the equation becomes gamma into V power gamma minus 1 dV into V power minus gamma is equal to minus dPP. So you have got two terms. One term is V power gamma minus 1 into V power minus gamma in the LHS. So simplifying this, V power gamma and V power minus gamma will get cancelled and you have V power minus 1. So the equation becomes gamma into V power minus 1 dV is equal to minus dP by P. V power minus 1 you can take it to the denominator. So the equation becomes gamma into dV by V is equal to minus dP by P. So rearranging this equation once again you get dP by P is equal to minus gamma into dV by V. Now our aim is to find the change in pressure. So the equation for pressure we got it as dP by P is equal to minus gamma into dV by V. Now V is the volume increased by 4% and gamma value is 1.4. So we have to find the percentage change in pressure. So we are multiplying 100 on both the sides. So we have dP by P into 100 is equal to minus gamma dV by V into 100. Substituting the gamma value and dV by V is the increase in volume which is 4%. So that also you have to substitute. So which is equal to minus 1.4 into 4. So the answer is minus 5.6. Since it is a minus, the pressure is decreased by 5.6%. The ninth problem. In a petrol engine, where internal combustion engine, air at atmospheric pressure and temperature of 20 degrees Celsius is compressed in a cylinder by a piston to 1/8 of its original volume. We have to calculate the temperature of the compressed air. And for air, the gamma value is given as 1.4. So here T1 is given as 20 degrees Celsius. This you have to convert it into Kelvin by adding 273. So the answer is 293 Kelvin. Volume is 1 meter cube. V2, the new volume is 1/8 of V1 meter cube. Gamma value is 1.4. Now we will use the adiabatic equation, which is T V power gamma minus 1 is equal to constant. So you can rearrange this equation for our given problem as T1 V1 power gamma minus 1 is equal to T2 V2 power gamma minus 1. Here our aim is to find the T2. So reversing this formula we get T2 is equal to V1 by V2 the whole power gamma minus 1 into T1. V1, the value you have to substitute it as 1. V2 is 1/8. So 1 divided by 1/8, the whole power 1.4 minus 1. So the denominator will move on to the numerator. So simplifying, you get 8 power 0.4 into 273, which is equal to 673.1 Kelvin. So this is the final answer. If you want, you can convert this into Celsius by subtracting 273. So the final answer will be approximately 400 degrees Celsius. Now the 10th problem. Consider the following cyclic process which consists of isotherm, isochoric and isobaric process which is given in the figure. Draw the same cyclic process qualitatively in the VT diagram where T is taken along x-axis and V is taken along y-axis and analyze the nature of heat exchange in each process. So first we will consider the process from 1 to 2. 1 to 2, if you see the diagram itself, you can understand that the volume is increased. So the heat must be added. Second process from 2 to 3. 2 to 3, volume remains constant. See that the line is parallel to y-axis. So volume is constant. First process 1 to 2 is the increase in volume. So increase in volume means heat must be added. For the process 2 to 3, volume remains constant. So there is an increase in temperature. The given heat is used to increase the internal energy. So for 1 to 2, it is a straight line parallel to the y-axis, and 2 to 3 also it is a straight line parallel to the x-axis. Now for the process 3 to 1, here the pressure remains constant, volume and temperature are reduced. So it is along the origin from 3 to 1. It is a straight line passing through the origin, and here heat flows out of the system. It is an isobaric compression where work is done on the system. Now the 11th problem. An ideal gas is taken in a cyclic process as shown in the figure. You are supposed to calculate the work done by the gas, work done on the gas and net work done in the process. We know that work done by the gas along AB is given by work done is equal to PdV, integral PdV. This is the formula. So pressure value from the graph itself, you can see the pressure value is 600. And del V, the change in volume is from 3 to 6. So the change is 3. So 600 into 3, which is equal to 1800 joule. When you can convert this into kilojoule, you will have the answer as 1.8 kilojoule because 10 power 3 is kilo. Next, work done on the gas, which is along the curve BC. So the area under the curve BC, or using the formula also you can calculate the work done, which is equal to P del V. Here the pressure is Along BC, the pressure is 400. Along BC, once again, the change in volume is 3. So 400 into 3, which is equal to 1200. Since the work is done on the gas, it is minus 1200 joule. Once again, you can convert this into kilojoule as minus 1.2 kilojoule, where kilo is equal to 10 power 3. Now the net work done in the process is given by area under the curve AB. Area under the curve AB can be divided into two. One area is a triangle and the other one is a rectangle. So the total area, you have to add the area of triangle and rectangle to get the total work done. So rectangle area, you know that it is L into B. Triangle area is half into base into height. So length value is 400, breadth is 3 and base is 3 and height is 200 from the graph. So substituting this, you get 400 into 3 plus half into 3 into 200, which is equal to 1200 plus 300, which is equal to 1500 joule, which is equal to 1.5 kilojoule. Now the 12th problem. For a given ideal gas, 6 into 10 power 5 joule heat energy is supplied and the volume of the gas is increased from 4 meter cube to 6 meter cube at atmospheric pressure. Calculate the work done by the gas, change in internal energy, and you have to graph this process in PV and TV diagram. So first we will start the problem with the given data. Q is given by 6 into 10 power 5 joule. Change in volume is given by 4 meter cube to 6 meter cube. So it is 6 minus 4, which is 2 meter cube. The atmosphere value is constant, which is 1.013 into 10 power 5 Newton per meter square. We know the work done formula as P into del V. Substituting the P value and del value, we get the answer as 2.026 into 10 power 5. This is the work done. Next, we have to find the change in internal energy. So for this, we used our first law of thermodynamics, which is del U is equal to Q minus work done. So substituting the Q value, P value, del V value, you get the value as 6 into 10 power 5 minus 2.026 into 10 power 5, which is equal to 3.974 into 10 power 5, which is approximately equal to 397.4 kilojoule. This is the change in internal energy. So first we will draw the PV diagram. Here the pressure is constant at 1 atmosphere as the volume is changing from 4 to 6. So when you draw the graph is a straight line parallel to the x-axis. Next we have to draw the VT diagram. Here pressure is constant at 1 atmosphere. So as the temperature is increasing, the volume is also increasing. So the graph is a straight line passing through the origin. Now the 13th problem. Suppose a person wants to increase the efficiency of a reversible heat engine that is operating between 100 degrees Celsius and 300 degrees Celsius. He had two ways to increase the efficiency. First one is by decreasing the cold reservoir temperature from 100 degrees Celsius to 50 degrees Celsius and keeping the hot reservoir temperature constant. The second way is by increasing the temperature of hot reservoir from 300 degrees Celsius to 350 degrees Celsius by keeping the cold reservoir temperature constant. Which is the suitable method? So in both the methods we will find the efficiency. Which efficiency is greater, that we will follow. So we know that heat engine operates at initial temperature at 100 degrees Celsius. So this you have to convert it into Kelvin, which is equal to 373 Kelvin. The final temperature is given as 300 degrees Celsius. So once again add 273 to convert it into Kelvin, which is equal to 573 Kelvin. So at melting point is 273 Kelvin. So the efficiency formula is eta is equal to 1 minus T2 by T1. Substituting the values, you get 1 minus 273 373 divided by 573, which is equal to 0.3491. So the efficiency is equal to 34.9%. So now first we are going to decrease the cold reservoir temperature and we will find the efficiency. So T1 is equal to 350 degrees Celsius. Converting it into Kelvin, we get 623 Kelvin, and T2 is equal to 100 degrees Celsius, which is equal to 373 Kelvin. Once again substituting these data in our efficiency formula, eta is equal to 1 minus T2 by T1, you get 1 minus 323 divided by 573, which is equal to 0.436. So the efficiency is 43.6% by the first method. Second method, you are increasing the temperature of hot reservoir. So T1 is equal to 350 degrees Celsius plus 273, which is equal to 623 Kelvin. T2 is equal to 100 degrees Celsius plus 273, which is equal to 373 Kelvin. So substituting these values in the formula for efficiency, we get eta is equal to 1 minus T2 by T1, which is equal to 1 minus 373 by 623, which is equal to 0.401. So the efficiency is eta is equal to 40.12%. So from this value of efficiency, we can find that method A is more efficient than method B. Now the 14th problem. A Carnot engine whose efficiency is 45% takes heat from a source maintained at a temperature of 327 degrees Celsius. To have an engine of efficiency 60%, what must be the intake temperature for the same exhaust sink temperature? So the efficiency of Carnot engine is given as 45%, which is equal to 0.45. Initial intake temperature T1 is equal to 327 degrees Celsius, which is equal to 600 Kelvin, adding 273. The new efficiency is 60%, which is equal to 0.6. So the efficiency of Carnot engine formula is eta is equal to 1 minus T2 by T1. So T1 is the temperature of the source and T2 is the temperature of the sink. So in case 1, we find the T2 value, reversing the efficiency formula, we find the T2 value as T2 is equal to 1 minus eta into T1, which is equal to 1 minus 0.45. That is substituting the first efficiency into 600, which is equal to T2 is equal to 330 Kelvin. This is the temperature in first case where the efficiency is 45%. Now for the second case, that is when the efficiency is 60%, we are calculating the temperature. So once again using the formula, eta is equal to 1 minus T2 by T1. Reversing this formula for getting an expression for T2, we have T2 by T1 is equal to 1 minus eta. So T1 will be equal to T2 by 1 minus eta, which is equal to T2 value is 330 divided by 1 minus efficiency is 0.6, which is equal to 330 divided by 0.4. Simplifying this, you get the answer as 825 Kelvin. So converting this into Celsius, you get the answer of T1 as 552 degrees Celsius.